Alright, let's get started with Lesson 5, Kinetic Molecular Theory. The kinetic molecular theory is going to help us to understand why the ideal gas behaves the way that it does. It also is going to help to explain Boyle's, Charles, and Avogadro's gas laws on a molecular or a particular level. So, to begin our study of the kinetic molecular theory, there are 7 postulates to that theory that you need to know and become well aware of. In fact, you should be able to state these 7 postulates in your own words and understanding. Okay, so the first one says gas particles are in constant motion and collide with the walls of their container, thus exerting a pressure. So postulate 1 explains to us why pressure occurs, and simply that when gas particles collide with the walls of containers, they're going to create a pressure with that collision. Now, postulate 2 says that the magnitude of the pressure is determined by how often and how forcefully the molecules strike the walls. So postulate 2 is very important because it tells us that pressure is determined by how often or how frequent the collisions will occur with gas particles and the walls of the container, plus how forceful those collisions are. And as you'll see as we look at the gas laws, Boyle's, Charles, and Avogadro's, that the collisions, how often or how frequent those collisions occur, will indicate an increase or decrease in pressure on our system. All right, so postulate 1 and postulate 2 kind of help us to understand pressure. Now, number 3 says the distance between gas particles are very large. And therefore, because of that large distance, gases are compressible. They can be compressed into a smaller volume. Remember that solids are their particles are very, very close together, and so solid particles are not compressible at all, whereas gases are. And liquids, to a very small extent, are compressible, but not very much, not near as much as gases are. All right, postulate 4. The attractive and repulsive forces between gas particles are very small. Therefore, gas particles are free to spread further apart. So, this goes back to understanding that an ideal gas is essentially going to have 0 intermolecular forces or 0 electrostatic forces between the particles. So this will allow those particles to be free to spread out and fill up the container or to move freely as they want to be. Postulate 5, the absolute temperature. Now, when we talk about absolute temperature, we're talking about the Kelvin scale. All absolute temperatures are in Kelvin, so you might want to make note of that. So the absolute temperature of a gas is a measure of the average kinetic energy of its molecules. All right. What this tells us then is that at a specific temperature, it will be associated with a specific average kinetic energy. In fact, in reality, temperature is a measurement of the average kinetic energy of a gas or liquid or a solid. All right. Number 6, if 2 gases are at the same temperature, then their molecules must have the same average kinetic energies if they're at the same temperature. And number 7 says energy can be transferred between molecules during collisions, but as long as the temperature remains constant, the average kinetic energy of the molecules does not change with time. In other words, it's just saying that as molecules are moving around randomly, and as they collide together, those collisions can result in a transfer of kinetic energy. However, that transfer of kinetic energy does not change the overall temperature of the system. Therefore, the average kinetic energy does not change with time, and we have a constant temperature. All right. So those are the 7 postulates to the kinetic molecular theory of gases. And again, make sure that you can state those 7 in your own words, specifically for the test or quiz that we'll have over this lesson 5. All right, so let's take a look at a diagram of the kinetic molecular theory in action here. So I have a container of gas molecules, and these gas molecules are moving randomly. In fact, let's write that down, because I think that's an important thing to understand. Is that particles move randomly. As a result of the kinetic energy, I'm just going to do Ke for kinetic energy that they possess. Okay? I think that's important to understand, is that those particles are moving around fairly randomly. Now, we know that, as we talked before with the kinetic molecular theory, that when a gas particle hits the walls of the container, in other words, when it collides, so collide with the walls of their container, this is going to cause an exerting of pressure. Alright? So, again, when those collisions occur, pressure is going to result. Now, what is going to determine the pressure? Well, again, it goes back to the two things. How often these molecules collide. The more collisions, the greater the pressure will occur. The magnitude of the collisions, the greater the pressure. And that's what pressure is really determined by. All right. The gas molecules, I think you should know and understand that they are constantly moving. So the gas particles are in constant motion. Because they have kinetic energy. And also, super important, understand that molecules have very small attractive and repulsive forces. All right. I really think that these are some important ideas to understand about the kinetic molecular theory. Zero intermolecular forces or attractive forces constantly in motion, and when they collide with the walls of their container, they contain or they create pressure. And the more often those collisions and the higher the magnitude of collisions, the greater the pressure will be. All right. What we're going to do is change our attention to a very important distribution curve. This is called a Maxwell-Boltzmann distribution curve. And these curves are very critical in our understanding of chemistry. And we will use Maxwell-Boltzmann's distribution curves quite a bit. So I'm going to go ahead and draw some axes here. Actually, let me erase that and make that a little bit better. There we go. All right, so on the y-axis, we essentially are going to have, we'll label it as fraction of molecules Okay, fraction of molecules. And on the x-axis, we're going to say kinetic energy. Okay. So again, we have Y-axis, fraction of molecules, and x-axis is the kinetic energy. All right, now a distribution curve then it's going to look something like this. I'm just going to draw this out like so. Looks very similar to this. All right. Now, for those that don't really understand calculus very well, what this distribution curve is trying to show us is that this is a range of molecules at a specific temperature. So let's say that this temperature of this range of molecules is at 300 Kelvin. All right. Now the area under the curve, and I would write this down. The area under the curve, under the curve represents the total number of molecules. Okay, so if I was to actually find the area under this entire curve here, this would actually then represent all the molecules of our system. So say we have a container, and that container is at 300 Kelvin, and the area under the curve for this container represents the total number of molecules that are in that container. So I hope that makes some sense. So where's the majority of the molecules that are that have specific amounts of kinetic energy? And you should say that in this area we have the largest amount of molecules. And so I'm going to erase this here. We'll redo that curve a little bit. So right in this area right here is the greatest percentage or fraction of molecules that represents this amount of kinetic energy. And since that's the greatest number of molecules, that means at that point this is known right here as our average. So average kinetic energy at that temperature, at 300 Kelvin. All right. Now you'll kind of look at this and you'll see that even though we rewrite this down, you'll see that even though not all molecules have the average kinetic energy, there is a small fraction that have a number of molecules that are well beyond the average kinetic energy. So what happens then if we change the temperature? What would happen to this curve? So I'm going to show you another one. Let's use a different marker here. And what would happen is if the temperature increases, the curve is going to change slightly. The distribution. All right, and we'll say that this is now at, say, 350 Kelvin. So when the temperature changed, you'll notice that the average kinetic energy right here at the peak point has also changed. So we have a new average, and the average went up. And that should make sense because when we increase the temperature, there should be more molecules that have a greater amount of kinetic energy, and so a greater number or greater fraction of molecules should increase the average kinetic energy overall. All right, but you'll also see something else that will happen. As the temperature goes up, there becomes a greater percentage or fraction of molecules that have more higher kinetic energy. All of this right here represents the new amount of kinetic energy. So much higher proportion or fraction in this energy. So as the temperature rises, more molecules begin to have more and more kinetic energy, as shown by this Maxwell-Boltzmann distribution curve. Okay? Now, I know these curves are sometimes hard to understand, especially if your math background is not in calculus. So I'm not going to try to bring on much calculus into this. but so try to do your best. I will go over some more of the Maxwell-Boltzmann distribution curve in class and answer any questions that you might have on it. We will be seeing these, as I mentioned earlier, quite often in later units. And even later in this unit, we'll also see some more Maxwell-Boltzmann's distribution curve and the implications of what those mean. All right? All right, so what we're going to do now is we're going to finish up this lecture video on looking at gas laws and the kinetic molecular theory. Specifically, we're going to focus on how does the kinetic molecular theory explain particular gas laws. So we're going to look at Boyle's law to begin with. Now, remember, Boyle's law deals with the relationship between pressure and volume. As long as the temperature and the number of moles are constant. So let's write the equation real quick. So you know that P1 times V1 is equal to P2 times V2. Now, according to this equation, we should understand that pressure and volume are inversely proportional. As the pressure goes up, the volume goes down, or vice versa. Okay, and that's Boyle's law. Well, can the kinetic molecular theory help us to understand this relationship? Okay, so let's take a look at these diagrams of gas molecules. So here we have a container, and currently the outside atmospheric pressure is 1 atmosphere on that container. The volume and the temperature are listed below, so it's a 1 liter container at 298 Kelvin. And we're going to keep the temperature constant in this model. What we're going to do, though, is we're going to decrease the volume. So the volume is going to go down here. And what that's going to result is half the volume. So we're going to go from 1 liter to 0.50 liters. Now, what's going to occur then is that we have a more compressed gas. All right? Now we know that from our postulates that gases, because they have a large space between them, are compressible. And so that's exactly what's occurring here. As the volume decreases, the gas is being compressed together. Now, a compressed gas is then going to have basically more collisions. All right, there's going to be a lot more collisions that are going to occur at these smaller volumes. So what we're going to write here is that in a smaller volume, oops, I'm going to abbreviate volume. In a smaller volume, VOL, molecules, or we could say molecules will collide more often, okay, or more, okay, collide more often than at larger volumes. Now, you can kind of hopefully see this. If those molecules are compressed in a smaller volume they have more opportunities or a higher frequency to collide with the walls of the container. Now remember, going back to postulate 2, what determines the amount of pressure that a gas exerts is going to be based on how often or how frequent the collisions between the gas and the walls of the container. So the smaller the volume, the more collisions. That means the pressure is going to go up. And so what's going to happen is this inside pressure is going to increase. So the pressure goes up with the smaller volume. If we compress the molecules even more down to 0.25 liters, then we're going to even have even more collisions that are occurring with the walls of the container, and the pressure inside is going to go way up, super up. So here we see our inversely proportional relationship. The volume goes down, the pressure goes up. Because a smaller volume, there's going to be more collisions, and therefore more frequent collisions, a higher pressure. All right, so that's how the kinetic molecular theory explains Boyle's law. So make sure you understand that quite well. All right, what about Charles' law? Let's take a close look at what's happening with Charles' law. Remember, Charles' law deals with the volume of a gas and its temperature. And we know that the volume 1 over temperature 1 is equal to volume 2 over temperature 2. And we also know that when we do a curved line, we get a straight line, which tells us that temperature and volume are directly proportional. If the volume goes up, then the temperature is going to go up. Or we really should say, as the temperature goes up, it's going to create an increase in volume. So why does this occur? Why does, when we increase the temperature, the volume increases? Or we can look at it, why is it when the temperature decreases, the volume goes down? What's going on here? Well, let's think about this for a moment. If I increase the temperature, if the pressure is held constant, okay? In other words, we must hold the pressure constant. The pressure cannot change, all right, at all. So if I increase the temperature, so by adding heat, okay? By adding heat, we know that the temperature is going to go up, all right? Now, an increase in temperature is going to cause molecules to move faster, okay? So let's make note of this. Molecules move faster. Okay? As the temperature keeps on going up, the molecules move faster. Now, if the molecules move faster, then that means that they're going to hit the walls of the container more often. All right? So in other words, there's going to be more collisions. The faster the molecules are moving, the more collisions, or the more frequent the collisions are going to occur with these gas molecules in their containers. Well, you know that if the collisions increase, then that must mean that there's going to be a change in pressure. But wait a minute, we want a constant pressure. We don't want the pressure to change. So what does the system have to do in order to keep the pressure constant? Well, in order to keep that pressure constant, the volume must go up. All right? Now you know that when the volume goes up, the pressure is going to decrease. All right? And that was Boyle's law. All right? So there's kind of this coordination between Charles and Boyle's law a little bit. So again, as the temperature goes up, the molecules move faster, so they're going to collide with the walls of the container more. This would create a greater pressure. But we don't want the pressure to increase. We actually want the pressure to stay the same. So to alleviate that pressure, then the volume would have to go up. It'd have to actually increase, and then that would basically keep the pressure constant for explaining Charles' law. All right? And so we can actually, let me write some more on this. I'm running out of room, so kind of put this in perspective then. So right here, we're going to add energy, right? We're going to add energy. This increases the pressure. I'm just going to use P for pressure. Pressure of the system. All right? Increases the pressure of the system. And so the volume must, I'm going to write an arrow, go up increase to keep the pressure, P for pressure again, constant. Okay? So hopefully that helps to explain Charles' law a little bit. So one more time. I know I'm repetitive on this, but this is pretty important to understand because you're going to have to explain all this yourself on the quiz and test using the kinetic molecular theory. So again, as we add heat energy, the molecules move faster. So they're going to collide with the walls of the container more often. This increases the pressure. But again, we want to keep the pressure constant. So in order to do this, the system's volume is going to go up. It's going to increase. And by doing this, this reduces the pressure, and it goes back to our normal, keeps the pressure constant in this idea. All right? So that's Charles' law for us. What about Avogadro's law? Avogadro's law, there is some similarities with Charles' law here. Now, instead of increasing the temperature, though, or adding more energy, we're just going to add more gas molecules, okay? So what's going to happen is we add more gas molecules, there's going to be more molecules that can collide with the walls of the container, all right? So more molecules means more collisions. I would probably write that down. More molecules, more collisions means more pressure. Now wait a minute, Avogadro's law states that the number of molecules are going to change. Therefore the volume, in fact, let's write this down. So the number of moles goes up, or the number of molecules, that means the volume must also go up, okay? So why does the volume go up if I add more moles? What's going on? Well, again, more moles, more collisions. More collisions means there's an increase in pressure. But we need to keep the pressure constant. So what do we have to do to keep the pressure constant? We have to increase the volume. So the volume of the container goes up. That will reduce the pressure and keep then the pressure constant. So in other words, what we're saying is by increasing the volume, it will keep the pressure constant and obey Avogadro's law. All right, so again, let me repeat myself. This is pretty important to understand. Avogadro's law states this. When the number of moles increases, the volume has to increase to keep the pressure constant. And the temperature is going to maintain the same. But the biggest thing is the pressure being held constant here. So when we increase the number of moles, we increase the number of collisions between the gas molecules in the container. That results in an increase in pressure. All right? But remember, we don't want the pressure to increase. So we have to increase the volume. The volume's got to go up, and then that will reduce the pressure. Therefore, it will keep our overall pressure constant. All right? And that's simply how it works. I hope this makes sense to you. If you need to relook at this video, lecture video, I would encourage you to do so. You may need to take some time to really think about this and to work out Boyle's, Charles, and Avogadro's law to make it make sense with using the kinetic molecular theory. All right, we will have a quiz on this, and this is also very much a required objective for the AP and IB exam. So know it well. Come and see me if you need some help or if you have some questions, okay? So that is it for this lecture video.